Okay, so now that we've spent some time working on the project 3, I want to talk a little bit about it to hopefully cement some of the concepts in everybody's head so that you don't spend too much time wandering around confused. So for project 3, we're starting out with the project 2, right? And we're really just adding 2 modules to it. And I've seen some people combining the controller and the memory. You can do that, but it's not quite correct because the memory is not part of the controller. The memory is just a list of commands that is going to tell the controller what to do. Now, we had this data port, right? And that's the IO that we had before. And the memory also has the data port. So that if I'm pulling command from the memory, I assert the read signal, pretty much. I want to read from the memory. Whereas the write goes to the project 2, right, and says, I want to write to memory. Now, in both cases, it's this kind of mux configuration that we talked about, right, where one input is Z's and the other is R in this case, and I can't remember what they call it in that one. And so that's how they're talking to each other, is read and write. Now this data internally, right, connects to that internal bus. So the other thing that data does is it goes to the controller, because the controller needs to get the next command. So that's what we talked about in the lab, where we're going to build a state machine, right? And normally we have something that's like idle. But in our case, I used fetch. A better one is probably called get command is probably a better way to call it, right? Because that's what it's doing, is getting the next command. And it can be confusing because fetch is a signal that's going to the address, and I don't want that to get confused because they're different things. And what get command assumes is that the data in the memory is appropriately formatted. And by that, I mean it's a memory that starts off with a command. And if that command is an immediate, right? So an immediate command says the next thing in memory is going to get loaded into the system. So it goes command, data, command. If it's not immediate, right, that means it has to go get it from memory. So then what it expects, so command memory, is it expects something like a memory address, right? Where do I get this? And then so it gets the memory address, and then it has the load from memory, essentially, right? Go get that address, get that data out of memory. And the way it works, right, the memory address gets loaded into the MAR over that data. And then the load from memory says, okay, well, it's the MAR is saying, hey, this address this is my address that I just saved in the MAR. Put that address onto this data line, and I'll do something with it. But I don't want to be in get command at that point, because if I'm in get command, then I'm trying to use whatever that memory value is as a command, and that doesn't make sense, right? So that's where this kind of two-state comes from. If I have something that is something like load for memory, right? It's what memory address, what value. So if I get store to memory, it's the same kind of idea, right? I need an address. Where am I storing it? Here's the data to store. So if my operation, which comes over the data line, says store to memory, it goes to something like get memory location, store to memory, go back and be ready for your next command. Go get the next command. Now, obviously, this doesn't work if the memory is formatted wrong, right? So I've created the memory for you. You don't have to worry about formatting memory, but if you wanted to go back and create a memory that did a different application, a different program, right? Then you would have to change this and make sure that it fits the right format. Okay, so during this second step, this is, right, don't care. No matter what happens on the next block cycle, I'm going to move on to STM. And this is, no matter what happens, I'm going to move on there. And because we have the specification of an asynchronous reset, there's an implied this and not reset. But the reset is asynchronous, so it kind of overrides the whole system, so we don't really have to write it. Because if we reset, we want to go back to get command, reset the memory address, and we'll run the program again. Now, the other one that's been confusing people is inside of here. We have the ALU that has an op code, right? And it's confusing because project 2 has, op amongst other things, right? Where this op is some list of commands like ADDI or XORM or whatever, right? The op that we create in the constant in this project 3 are different than the op codes here, but linked, right? Because this controller is outputting the op code, and it decides what op code to put in. Oh, sorry, I put that on address, not on data. So it looks at the data, and then it moves into a state, like get the memory location, and asserts some opcode, which is only one of 5 choices, right, for the ALU. Whereas the opcode that goes onto the data is like one of 12 or 14. I can't remember exactly the number. And so it's bad naming, unfortunately, really, because it can get confusing that this op and that op are different because they're both op underscore somethings. But this is just the list of 5 that you did in project 1. This is the list of 12 that you're making in project 3 that tells this which state to jump to. That's all. Is you're looking at that command that's coming out of memory onto the data line, saying, oh, I'm supposed to do that. So what happens, right, is this sends out, in that case of that, sends out the fetch command, right, to switch to the MAR. And it also sends out the load MAR signal so that it can update with that memory address, right? So we were here and moved to the state memory location. The PC increments. So we go to memory address. We assert load MAR. That loads the MAR in to there. The PC increments. And now we go to load memory, which is where we switch the PC off. We're no longer counting. We turn on fetch, right? So we use the MAR and set the PC. And then the thing that appears on the data line is whatever value is stored at the memory location this memory address holds to. And the opcode that gets sent out is just hold, right? If we're loading or storing, well, if we're storing to memory, it's hold, right? Just hold on to the data while we load that into this memory. If it's read from memory, then it's load. The opcode is load, so we can take whatever data value is put on here and put it into the accumulator, right? And remember, that's important. That the stuff that we're loading or storing is all coming out of the results of the accumulator, right? Because that's what's being put onto data. Okay. All right, that's, I think, what I want to talk about that with is just focusing on there's these 3 blocks. get the ports right, and we compare the ports that are on the output controller and what is asserted, well, just directly from project 2's test bench. You don't have to go and figure out is load var asserted, as long as you pay attention to the commented blocks, right, that are like, this is ST, and it says O, but it should be M. Stored to memory, it'll give you like the location 3 app or something, and it'll store the value, whatever it is, and then it'll give you that list of commands of how did it store, and you just make sure that they get asserted, and you know that each state requires 1 clock cycle, so if it says wait for 10 nano, that's a clock cycle, right? So we did something, we wait, we do something, we wait. And that's, we can kind of tell how many clock cycles each of these operations. Okay. I almost forgot by way of announcements. I had it pointed out to me by you guys on, well, yesterday, that the core valves weren't there. They should be up and good to go now. They should be fixed. Some of you, it may take till the end of the day before it's updated, but we've also extended the deadline for them to be done for those ones. We don't know what happened. It's just a couple of ECE classes had a weird error. They'll be up. Okay. So the next thing that I want to talk about is other uses for state machines. Because I've talked about it as the controller, right? And I've talked about it as a sequence detector, which we'll do another one of those examples after this one, just because they're good examples. The state machines can do some useful things. And I'm going to go back to our garage door opener for an example. Okay, so I had you guys implement the garage door opener on an FPGA that has a clock at 100 megahertz, right? And I haven't taught you guys how to change clocks on an FPGA because, well, we do that next semester. Well, whenever you take 3610. So we're stuck with 100 megahertz clock. But you and I, nobody is fast enough to push a button at 100 megahertz. So if I have the clock and the button, and it comes along and the button is pressed, right? And I start and say ready to go down. Well, I push that button, I start going down, I stop going down, I start going up, I've unpushed the button. And really, since we don't have like precise timing on it, no matter how hard we try, pushing the button on that FPGA would really be like a random function generator. We have no idea how long we've pushed that button. So what we want is to generate only 1 pulse for each time I push the button. Now there's a couple of ways to do this. You can actually use just 2 flip-flops in series that do that if you wire them up, right? But let's go ahead and build a state machine that is going to go ahead and do this. And as usual, we're going to start out at some idle state that I'm just going to call I. And then I'm going to go into I push the button state. Now in that button, I push the button state, I'm going to have an output. So I'm going to build this as a more state machine, right? That's what this notation means is for. So this transition happens when button, right? So I push the button, I go here. During that, I'm going to have my output Z go high. Here is explicitly not Z, right? And then I'm going to go to a third state. It will become parent Y in just a minute. State wait, that is not Z. And then I go back to I only when not button. This is don't care. Right? So that's 1 clock cycle. So what happens is I push the button. On the next clock cycle, I jump into B, assert my output Z. And actually before that, I'm going to do state and then Z. On the next clock cycle, I move into wait, I deassert my Z, and then I go back after I've released the button and I'm ready to respond to another button push. Okay, so the state changes on this rising edge. Right, and so here I'm in that idle state. Here I'm still in idle. I've got a clock with the button push. That means I go to state B. And then I said, no matter what, I move on to W. So I, B, W. I get another clock with the button is still high. It's still waiting, right? And that would wait for as many clocks as I have where the button is asserted. But this time I get a clock and I'm no longer asserted. So I move from W back into I, ready for my next button push. Well, Z then is high during B and low everywhere else. 1 pulse. Right? So that's how we can kind of deal with this higher speed system with the low speed input. It's just a simple 3-state state machine. But there's a problem with this. Does anyone see the problem with Z? Think about it in terms of non-ideal circuit behaviors. What happens if this gets a little bit of jitter, or moves one way or another, or it has a little bit of clock delay and goes a little bit long, right? Then we would see 2 button pushes here, because I've got 2 clock edge. And this one is what we call that race condition. We don't know if this one's going to trigger or not. And we don't know if this one's going to trigger or not. Now, in a real system, it's really going to be shifted a little bit this way, generally, which is going to result in 1 probably, but not always. We're at a high risk for missing this pulse because of the race condition. Because this clock is going to be feeding both, like that's the master clock. It's going to be controlling this state machine and whatever is looking at this output. And that's a problem. But we can fix it really quite easily. Because if you remember, when I have you guys assert input changes, I tell you guys to do it right in like just a test bench. We want to center on, so I have some input I. If it's high, drop to low. If it drops on the falling edge of the clock, right, then it is as far away as possible from either rising edge, right? So this is the safest place to make a transition because it gives you the maximum opportunity to deal with clock delay, for example. So this is a great spot to do it. Well, we can do that with this state machine. Simply by triggering out the falling edge. So when I build this state machine, not clock, right? Falling edge triggered clock. And the reason is then, well, same thing happens, right? So I start, I'll call this not Z, right? This is kind of, it's not really true. The Z tick, that's a good one. Okay. So the states then are still idle till here, but I get a falling edge. I'm still idle, falling edge with a button. I move to button, which is this whole range, right? And then I move back into wait. Okay, well, march along, go into button, come out of button, stay low. Now, my rest of my system, right, which is rising edge triggered, sees this clock edge. right in the center of that button search. So its delays are really robust against any sort of non-ideal circuit behavior. So that's one way that we deal with this. But we got to be aware of problems like potential race conditions. There's a chance, I think it's kind of low, that we'll get to go back and put this garage door opener onto an FPGA. If we do it, you'll end up having to use something like this because we have that, I think it's a 5-button input on the FPGA that looks something like that. We'll just assign one of these buttons to be the button input, and then it'll go through this transformation and output like button in, Z out, right? And then to visualize the garage door opening, you take those LEDs that are along the bottom, right? You got, I don't know, 12, 16 LEDs, I think. And like you'd push the button and it would start going up, right, by lighting up the LEDs. And to do this, you have to build a clock divider, right? Because we're going from 100 megahertz clock way down to something human perceptible. So we have to build a substantial clock divider. So you do it, you push the button again, it stops, push it again, it starts to open back up. That's how we would do that on the FPGA. We might get the chance, but we are about out of time, right? So the last day of class is the 26th, which is a Monday. We don't have lab on that Monday. So as far as this class is concerned, you guys are done on the Thursday of next week. For Monday of next week, we will have lab and we will just be working on project 3 so that you guys have plenty of time to get that done because it's important. And we'll talk more about microprocessors in 3610 as well. So they come back, don't worry. All right. Let me go ahead and move the camera. And I'll continue on theme, talking about other issues in state machines. Remembering that state machines, we can generally look something like the following, right? Where I have a series of D flip-flops that hold my current state. The output then is current state, right? That's what they're paying attention to in the output. That goes into some output decoder that has our outs. It also feeds back around into our next state decoder. This input here is our next state, right? So this is combinational logic that depending on our inputs, however many bits they happen to be, put in some inputs, uses whatever state we're in and those inputs to output the next state. This clock happens and then loads next state into current state. Once that's loaded, output decoder does its thing in the current state. In a Mealy type machine, we have that extra path, right? Because the output depends both on our current state and our input. In More, we don't have this forwarding path. Okay, so that's our basic building block of a current state. But let's say that we want to run this circuit fast. I've talked about it before. This net state decoder has combinational logic, and those gates are not ideal, right? They have some form of delay. So if I'm running really fast, current state updates, feeds it back around to next state. The next state logic starts to work and starts changing its output, but then the next clock hits, and we haven't changed yet. So our next state then gets loaded in, but it's not ready, it's not stable, and we load into some random state. Well, that can be a problem. Another problem can be what we call a glitch, which is where the output value of our combinational logic spends a little bit of time being something that it's not supposed to be. Now, glitches are a physical phenomenon that results from having a hazard in the circuit. The hazard being a potential for error. There are two types of hazards that we are concerned with. One of them is a static hazard and one of them is a dynamic hazard. Now, the static hazard results when my output on a gate should stay 0 or should stay 1, but it doesn't. A dynamic hazard happens when we are going from 0 to 1 or 1 to 0, but instead of doing that just once, it happens multiple times. So like if I'm trying to go 0 to 1, it goes 0, 1, 0, 1, right? Kind of bounces. Both of those things happen. Now, the nice thing is, if a circuit doesn't have a static hazard, it won't have a dynamic hazard. Now, we can talk about dynamic hazards in more detail in 3610, I think I will. For here, I'm going to focus on static hazards because they're a little bit easier. And it's still just using the same skill set of the timing diagrams that I've thrown on both tests, right? First test didn't have delays, this one does. I'm just going to pull my example just so you guys can later go back and look at it from page 642. I'm pretty sure that's the one. Yeah, okay. So if there was, right, so when we do this design, when we make this next state logic, we start with a K-map. So let's say that we had a K-map that's 3 variables that is A, B, and C. Is that too small or is this okay? Okay. Right. And if I asked you to design a minimum circuit for this, you would just go into the K-map, you'd say, aha, that and that, right? And this is 2 AND gates that go into an OR gate, right? We know that. And I'm actually going to swap the A and B's just because it makes it easier. Right? So that's our circuit. This is like if there were 2 inputs and only 2 states or something, right? That's a really kind of weird example, but it could work. Now, a hazard exists, can only exist if one input signal has multiple delay paths. So only one of these signals has the potential to have an error, BA, right? Because it has a delay path of 1, 2, 3 gates, or 1, 2. Both B and C have a delay path of only 2 gates. Okay. Now, you could, well, you should go ahead, and the question I would ask or something on an exam is going to be throw up a circuit or throw up a K-map and then tell you to find the static hazard. Now, there actually ends up being a really easy way to determine if a circuit has a static hazard, which I'll get to in a bit. But for now, we need to talk about this really important concept called priming the circuit. And now what priming the circuit means is that we need to get it ready to respond to the potential problem. So we know by looking at this that A is the potential problem. So how do I get it ready to respond to that problem? Well, if B is 0 and A changes, the output of this gate, which I will call D and this one E, if B is 0, A cannot affect this output of this gate. If C is 0, A can't affect the output of this gate. So in order for the circuit to respond to A, we have to prime it by allowing these gates to respond, which means just setting B and C to 1. Right? Because then the only thing that matters what B and C are one is what is A doing. Now, in an OR gate, priming the circuit is different, right? Because in an OR gate, if I had an A and B was 1, A doesn't matter, right? Because it's always going to be high. So in an OR gate, priming a circuit means 0. But we only need to prime our inputs. We don't need to like artificially force E and D, right? We just control the inputs. That's all we have control over. So we set B and C equal to 1. That's the big part of it, is identify what do our signals need to be. Then we pop over and we say, okay, we're going to use a timing diagram to identify the problem. Well, let's do this. Okay, so I said B, 1, C, 1, A. Okay, A is what I need to change. So if you're unsure, a really good way to do it is give it one change of each type, right? Go 0 to 1 and then 1 to 0, because we're either going to have a static 0 or a static 1 hazard. Static 0 means that it's supposed to stay at 0, but it glitches up to 1 for a little bit. Static 1 says it's supposed to stay 1, but it glitches to 0. Now, we can see that in the circuit really easily, what it's supposed to do, right? So if B is 1 and C is 1, and A is 0, then D is 1, making F 1. If A is 0, A bar is 1, E is 1, F is 1, right? So in this primed circuit, regardless of what else we do to A, it should say 1 as the output. It should static 1, right? Okay. So let's go ahead and say that my divisions here are 20 nanosecond intervals. And let's say that my gate delays are 10 nanoseconds. Well, if I don't have gate delays, I probably don't even need to bother drawing a bar. But I'm saying that all gates have this equal delay, which I want to point out is a little bit unreasonable because there are fewer delays in an inverter than there are in an AND gate. But just for simplicity, we'll say they have 10 nanoseconds. So that means that A bar is equal to A with a 10 nanosecond delay. Okay, so A bar is, well, sorry, is equal to not A. Right, that's 10 nanosecond delay. So it takes a little bit for the A bar to update. Okay, well, now let's go ahead and do D. D is pretty easy because D is just saying, well, B is 1. So D is the output of A and 1, or in other words, just A with a delay of 10 nanoseconds. Okay, so D goes and says it's not A. It's a delay. It's a delay. Done. So it turns out with this prime circuit, D is the opposite of A bar with no delay, right? Coincidental, that's fine. Now E, the output that is considering A bar and C. The C is always 1, so we care about A bar with a 10 nanosecond delay. Okay, so A bar is 1 here, but I need a 10 nanosecond delay. So then it drops. And then a second delay after its change goes back to 1. Okay, now F is just D or E with another 10 nanosecond delay. So if D or E is 1, F is 1. So E is 1, E is 1, E is still 1, and D is 1. So we're good. Well, let's look here. D has dropped to 0. E has dropped to 0. So I get a 10 nanosecond window that its F is 0 with a 10-second delay. So F is supposed to stay at 1, but it didn't. Because A has 2 different delay paths, and we didn't, one of those doesn't update to cover the other one fast enough. Right? Because we're changing from this path to that path of which one is on. Because this was 1, right? So this was a 1. It changes to 0. So this updates really quick. This one updates slower to 1. That's what's happening. So that's what we call the hazard causing this little glitch. Okay. But what's nice is it turns out it's very easy to determine if there is a hazard in the circuit and very easy to fix it. The way is we go to the K-map, and if the K-map has adjacent ones that do not share an implicant, right? An implicant means one of the circles. So adjacent ones that do not share an implicant, then we have a static 1 hazard. No matter what, it's there. Well, actually, I think there's a few exceptions, but you probably have one. Similarly, if you were circling the zeros, which I have you doing one of these, and you in the homework that I assigned that are adjacent. So if I had that, right? That's a valid K-map for black circles. But this 0 and that 0 adjacent and do not share an implicant, then I will have a static 0 hazard. And if I ask you to identify the hazard using a timing diagram, this is what you do. Draw the circuit, do the timing diagram, you know it should be there, right? The way we fix it is really easy. Is we just introduce a new path. Something that happens in the event that the 1 to 0 shouldn't trigger. And we do that reliably by adding an implicant. So this extra implicant means I no longer have the minimum circuit, but I have a hazard-free circuit. So there's a trade-off, right, between the complexity of the circuit and the robustness of the circuit. So if the most important thing is for it to be small, I would probably build that. If the most important thing is for it to be hazard-free, I would do this. That all that does is it adds an extra AND gate, right? And in this case, it happens to be B and C.
Would you have to do that with every adjacent one?
Yes. Yeah. So if you had a bigger K-map, you need more additional circuitry. I probably won't do anything terrible like that to you for this. Yeah, then you just do that K-map, add the circuit. Now you'll notice that B and C is going to be true because I primed the circuit with B and C as 1 that clearly goes away. And moreover, I also have no other remaining signals that have multiple varying delay paths. If you want to make the problem more difficult, right, maybe this, you could change it so that like an AND gate has a 10 nanosecond delay, this has a 5 nano, right? That could be annoying like that. I probably won't. I will probably stick to universal gate delays. But anyways, that's hazards. I think there's another example in the book. On page 646 that talks about the static zero hazard. If you guys need more example in practice. Okay. So now, the next thing I want to do is I just want to do another sequence detector example, just so you guys have some practice at it while I'm around. So the question that I would ask on the exam is, please design me a circuit that can detect the sequence 11010. Now, the way you do this, and I probably did like specify because I don't want you skipping steps, technically could. I would say something like, design me a circuit that detects 11010, start by creating a state diagram, then a state table, then build the circuit, right? So let's walk through this. I've done this kind of state design before, but let's do it again. I want you guys to start, because I talked about how to do this, design the state diagram for me. And I'll jump in and I'll do it up here in just a moment so that no one gets too far astray. The big hint, right, is start with the correct path, right? Then go back in and build the alternate paths. And design this one as a Mealy state machine rather than Moore. All right, so here, just real quick, is the correct path, right? The state machine requires 5 states for this detector. More takes one more than that, takes 6 because I need to detect some stage. 1, 1, 0, 1, 0 with the detect. Now, where do I go on the output of E? I do. Because if it was 1, 0, right, is my detection 1, 0, then I would jump back to C. But it's not, it's 1, 1, 0. We go there. Now, the rest of these, A is the other easy one, right? It's just 0. And B is the same thing, because if it sees a 0, there's no pattern there. But if I'm in C, I went 1, 1, and I see another 1, where do I go? I stay at C. Because think about the sequence 1, 1, 1, 1, 0, 1, 0, right? So it's A, B. So really it's, I'm sitting in A, I see a 1, so I get B, C. And if I go back to B, B is saying I've seen 1, 1 in a row. But I haven't, I've seen 2. Here, I still haven't seen 1 in a row, I've seen 2. Right? So as long as I keep seeing 1s, I want to hang out in C. Now D, we've got 1, 1, 1, 1, 1, 0. Well, what happens if I see D at 0? I restart. Yes. Yes, because I've seen 1, 1. I'll figure that out. Oh, no, because you've got the 1 here and then the 1 in the E. That's 2 1s in a row. Yeah. Yeah. It's always good to go back and throw some example patterns in that have, mistakes in them on purpose and check that you end up right. I will either specify, generally speaking, overlapping or non-overlapping sequences. If it doesn't say assume, I expect overlapping sequences. So, meaning like if I have 1, 0, 1, 0, if my detection was I want 1, 0, 1, 0 instead, I would want that detection and that detection. It's the default, right? Overlapping sequences. That's what that is. Okay. So the next step is the state table, where we take current state, next state, and the output, which I'll call Z. Now the current state is really 2 different things, right? First off, it's the A, B, C, D, and E, the names. But those names are merely representing the next state bits. So how many bits do I need to represent 5 states? 3 bits. There is a whole half a chapter or something in this book on state optimization, how you choose them. That's not really my focus here. So if you just go ahead and list them sequentially, I'm perfectly fine. Now, the next state always depends on both where are we now, what's our current state, and what is our input. So we do for z equals 0 or 1. And the output z is the same thing. Oh, sorry, not z, I. I equals 0, I equals 1. I equals 0. Well, let's start with z, because it's easier, right? It only outputs a 1 if I'm in E, and my input is 0. Everything else is right? So, oh, and before I forget, just for grading's sake, if you guys screw up the correct path, you're gonna miss a lot of points. Just because that's the one thing that's really important, right? If it doesn't do the bare minimum, you have a problem. If you get that thrown in there, everything else, I'm much more lenient when you start making mistakes on. But make sure you get the correct path right. Because if that's screwed up, it's really hard for me to give you partial credit because I'm like, I don't even know what you did from there. Okay. Now, the next state is a little more complicated, but not too hard if you've drawn the diagram, right? Because it's just a matter of where do we go? Well, if I'm in A and I get a 0, I stay at A. If I'm in A and I get a 1, I go to B. B is A or C. C is on a 0, I go to D. Otherwise, I stay at C. D on a 1, I go to E. Otherwise, A. And at E, on a 1, I go to C. No, I got off a little bit. There we go. A little more clear. Okay. I'm sorry. So D, if I'm 0, I get an A. 1, I go to E. E, I either go to A Okay. So I have 3 bits for my next state logic and 1 bit for my input logic. Therefore, my next state logic has 4 bits of input. That means a 4 variable K-map. The number of variables in your K-map is the sum of the number of bits in your state plus the number of bits in your input. I will not give you 6 bits. I may do 5. I will try and stick to 4, but if I come up with a really interesting problem, sometimes I'll do 5. But I'm not going to do a 6 variable K-map on you after this. Okay, so let's start with the output because it's easy, right? And if I call the variables S2, S1, S0, now there's 2 ways to do this. The first one is just to look at it. Because in this case, when there's only one situation where the output is true, it's very often easy just to build the logic. They want to see what Z is. Right, but what is the output logic? for Z. When is Z true? Well, Z is true if current state is 1, 0, 0 and input is 0, right? So if I were to go find this on there, is S2 is 1, everything else is 0. So S2 is 1, everything else is 0. There, right? And more than that, any state that goes beyond this is a don't care. Did I do this wrong? Okay. Right? Because 1, 0, 1, I don't care. So 1, 0, 1, 0, 0, 1, don't care. 1, 0, 1. Oh wait, actually 1, 0, 0, 1 is a 0. Because of that, right? That's 1, 0, 0, 1 is a 0. But after that, it's don't care, and I know all of these are zeros. And then I jump in with my K-map, right? Utilize those don't cares. And this tells us what you can actually see, right? Which is, well, the output of this is only an AND gate because it'd normally be an AND and OR, but there's no OR. And so it's only an AND gate with an input of, well, S2 and not I. Well, we can just see that, right? Because this is the only place where I have an S2. The only time this happens is if I have an S2 and I have 0. So it is actually possible to just jump straight to that gate in this case. And in many sequence detectors, in fact, it is very easy to do. Oh, look, depending on how you choose your state variables. Like, for example, if it's a four sequence, right, a 4-bit sequence, and your final bit is 1, 1, then your output logic is always going to be S1 and S0 and I0 or 1, right? It's always going to be a 3-input AND gate. Assuming I only have one output, yes. Okay, now, how much time do I have? Now these are a little bit more obnoxious, right? Because I have to go back in and keep in mind the you don't have to explicitly write them out. I find it helpful to not get distracted, right? Because these are the values of these states. How many K-maps do I need in order to make the next state logic? Yes, 3. So I need 1 K-map for each bit. So I just go ahead and I say, well, let's start with S0. And we can quickly discover the pattern, right? So we're 0, 0, 0, 0 is always this top left corner. That one's always the easy one to find. And my next state is 0. If I is 1, so 0, 0, 0, 1, this guy, it is 1. Right? Everyone sees that? Then we go 0, 0, 1, 0, 0, 0, 0, 0. Don't care, don't care, don't care, don't care, don't care, don't care. Right, and then I just do this case, which looks something. Unfortunately, this one is not very simplification friendly. And we draw this logic for that. And for S1, we do the same thing. And we just follow along. I already know the pattern. So 0, 0, 0, 1, 1, 1, 0, 0, 0, 1. Right. Now, we can kind of start seeing that maybe this isn't the best choice for the state assignments, right? Because I have all of these don't cares that aren't really doing me any good. And they're not really helping me much here either, because I get, well, actually this one's a little bit better, because that gets those two, that gets those two, and then I have that. And let's go ahead and look at S2 just to finish this off. Oh, well, S2 is going to be a weird one, right? Because it's always 0, actually. Right? The next state decoder on the third bit is just 0. I never go to a 1, 0, 0 state. Oh, here. Good catch. That makes sense. Okay, so I need a 1 at, where are we? So 0, 1, 1, 1. That one. And then the don't care stay the same. And everything else is 0. So anyways, I don't expect you to do the state minimization with this, right? Because you can kind of imagine there's probably a way to get these don't cares more distributed. That's a more useful way, maybe, that ends up with slightly simpler logic. I don't know for sure, but generally, if I skip to the 1, 1, 1 on this, that will happen. Not always though. Okay. From there, right? So the next step, I won't go through it, but you've drawn the circuits for this one, right? You got the K-maps, write the expressions, draw the circuits. Then once you've drawn the circuits independently, you just draw an arrow and say they go here, right? And the output logic goes here. And you're done. That's what that question is asking. When I asked you, design me a circuit that detects this. Those are all those steps. You will see something like that on the exam. It may not quite be a sequence detector as bluntly as that, but it'll be that kind of idea where you're going to get like a series of steps that it has to do, right? It could be like a story problem. And then you just write the correct thing, fill them back in, do the table, do the K-maps, done. If you're comfortable with that, you'll be able to do it really quickly and it won't be a problem. If you're not comfortable, this will take a large chunk of your final and you'll be sad.
What day is the final?
I don't know. I'll have to check. I haven't looked at the final schedule yet. After the 26th sometime. We'll do a review on the Thursday before the 26th, whatever date that is.
I have a quick question. So how much time do we have for finals? Just that one class?
It's 2 hours.
2 hours.
So yeah, finals are a little bit different. They'll give us a room, probably here, and a specific time, probably in the morning. And they'll say you get it for 2 hours. Other questions?
I remember, did you say this was a Mealy or Moore state machine?
Mealy, which you know, right, because of the way I did the output. Whereas a Moore, I would need a sixth state, because in a Moore state machine sequence detector, I need a state specifically for the detection, because the outputs only depend on the state. Right, this is a great visualization of that, right? So here, I care about the state that I'm in, E, and the input, 0. If I don't have Mealy, if I'm a Moore, I have to go to a specific state to assert the detection. So that would be state F, and I would have Z. Yes. So I could ask you, right? That would be the other way, because I'm not going to give you exactly the sequence detector. That's too easy for the final. But that is one valid type of twist, right? Is go, design me a Moore state machine. That does simplify it in one way, though, right? It adds complexity in the sense that you have to have an extra state. Adds simplicity in the fact that you no longer care about the input. For the output decoder. The output decoder gets easier. If that's all the questions, you guys are free to go. I do have office hours in like 15 minutes. I'll be over there. And I think I have some in the afternoon too. You can check the syllabus. I'll be in my office anyways. From 10:30 to noon and from 1:30 to 2:30. You guys can come to the project. If I'm not in my office, that's probably because I'm in the lab helping someone in there. I'll try and leave a note on my whiteboard outside the office. Have a good day.